Europe, the crucible of Western civilization. Steeped in history, from the monuments of ancient Rome to the castles of England. But Europe's last 200 million years point to a violent past. The Earth beneath us is moving with cataclysmic consequences. Continents rip apart in explosive eruptions, slam together forming vast mountain ranges, and shake the landscape in deadly earthquakes. No force has played a greater role in the birth of Europe than the movement of the Earth itself, when continents collide. Europe is still on the move, and southern Spain has had a violent reminder. A terrifying earthquake.
People were running all around, and the walls were collapsing.
10 people dead, dozens injured. Churches and homes destroyed in seconds.
When the earthquake started, I thought it was the end of the world. I fell down and I was worried for my family.
Hundreds homeless. A nation in shock.
The earthquake was so violent, it destroyed our lives, and sometimes we feel like crying.
Measuring 5.1, it's the worst earthquake to hit Spain in half a century. But it isn't the first time the ground has betrayed the people of Lorca. Earthquakes have shaken the area for the last 5 million years. Some over 20 times more powerful than this. Geophysicist Ramon Carbonell has spent 20 years studying the movements of Europe. The May disaster set him on a mission to find the cause of Lorca's shaky past.
Hi, how are you, Ramon?
2 Lorca experts have joined his investigation. The landscape looks normal to the untrained eye, but to the rock detectives, it's a hotbed of clues.
This one, and we were lucky this time.
Can we take a look?
Yeah, let's go.
Scouring the landscape, Ramon makes a breakthrough. An outcrop of 2 completely different types of rock lying side by side. Yellow continental rock crushed against green marine rock that is 12 million years older.
And the epicenter one.
This is a fault line. Fault lines and earthquakes go hand in hand. Imagine the planet as the size of a football. The outer crust is then no thicker than a few sheets of paper. Immense slabs of rock called tectonic plates float around the globe, carrying the continents. Blazing heat from the Earth's core keeps them constantly on the move. And sometimes they collide, fracturing the Earth's surface and crumpling up like a geological car crash. The fault lines are created by the impact. Rocks on each side scrape past each other as the plates push onwards. But in cases like Lorca, friction builds and the plates get stuck. Tension and stress build until something suddenly gives, and 2 landmasses violently jolt past each other. This is an earthquake. The May earthquake moves the entire city 20 centimeters in less than 10 seconds. Ramon is on a mission to identify the fault responsible. He's found his prime suspect. But to prove its guilt, he must follow its green trail and see what lies in its path.
This whole area is an earthquake zone. And I brought with me some new to trace the fault line.
Hilly terrain makes following the fault from ground level almost impossible. But this mini helicopter can trace it with ease wherever it may lead. It's the first time this technology has been used to map a fault line. Ramon locks in GPS satellites, fixing the helicopter's position while he studies the fault below. His eye in the sky soon reveals that one target is clearly in the fault line sights. The sinister line of green rock is heading straight towards the waiting town of Lorca. Ramon is tracing the path of the Alhama de Murcia fault line, one of the most active in Europe.
This is a classic example of a city being built on top of an active fault zone, which is the reason for all of this destruction.
Lorca sits on the southern edge of the European plate. Millions of years of grinding against neighboring plates have crisscrossed the landscape with thousands of faults.
Faults like this one are key features that shape the landscape of Europe.
Predicting which fault might cause the next catastrophe is a near impossible challenge. Geologists must first understand past earthquakes before they can predict future ones. Digging into a fault can tell geologists when it last moved.
Wow, here is it, huh?
The fault is very clearly marked here, as you can see. And it goes all the way till the surface and up to the mountains.
Two totally different rock types lie side by side. This rock is a mixture of clay and lime, once deposited under the sea. This rock is made of sand and siltstone, deposited on land.
We've taken a few samples for carbon dating, and we think the last big earthquake has been within the last 1,000 years.
Was that supposed to be larger than the one we felt?
Yeah, much larger.
This fault is giving up its secrets. Its rocks reveal that it's caused far greater earthquakes in the past. Some releasing 30 times the energy of a Hiroshima-sized nuclear blast. The entire southern boundary of Europe is an earthquake waiting to happen, a bomb that's impossible to defuse. But this modern danger is kindergarten compared to the titanic events of Europe's past. Scientists are piecing together the clues of Europe's journey back through time. From the devastation it's causing human life today to its prehistoric origins. Through a 200-million-year journey, Europe has repeatedly slammed into or been ripped apart from other continents. We're going back to the beginning of Europe's Odyssey, to the event that first binds the rocks of Europe together and changes the face of the planet. It's a tectonic event on an almost unimaginable scale. Every landmass on Earth collides. A single supercontinent, Pangaea, is born. Scientist Ricardo Amirs is investigating this mega collision.
400 million years ago, it was a big collision between two supercontinents. The evidence of this collision, we can find it here in the southwestern Spain.
It's hard to believe this is the battlefront of the greatest collision in Europe's history. 1,600 million tons of metal ore lie just beneath Ricardo's feet. Imagine 250 Egyptian Great Pyramids buried beneath the surface. Humans have been exploiting this geological treasure trove for the last 5,000 years and are not stopping now. Even the nearby Rio Tinto, the Red River, is colored by the many metal ores it carries. The size and date of this deposit point Ricardo to one event: Pangaea's formation. As the continents collide to create Pangaea, things get hot, very hot. Water in cracks in the Earth's crust superheats to more than 400 degrees Celsius and expands up through the rock. Metals within the Earth, like gold, silver, and copper, are belched to the surface by the superheated water. The titanic collision that creates Europe also lays down its largest metal deposit. Metal ore and civilization are inextricably linked.
Without mines like this, the Industrial Revolution would have never taken place in Europe.
The wealth and technology making Europe a global financial center directly relate to its geological history. Pangaea unites the rocks of Europe. Every inch of Europe's future coastline crushes up against a wall of rock. So how does Europe break free? The answer comes from an eyewitness. A witness living 240 million years ago. Something's walking across Europe as Pangaea breaks apart. Dr. Lionel Cavin is a paleontologist from the Geneva Natural History Museum. He's investigating how Europe escaped from the supercontinent. It's rare to find evidence of this 200-million-year-old event, but the mountains of Switzerland hide the strangest of clues. Near the village of Les Maricottes, Lionel finds sets of ancient footprints.
You see, this is one track right here, and another one just above.
They are 240 million years old and impressed into solid rock. The footprints were made in wet sand, which then hardened to become sandstone. These prints are a new, never-before-filmed discovery. More importantly, they are significant clues as to how Europe is as those of a giant reptile living 10 million years before the dinosaurs. His prime suspect, a near relative of Opisthosuchus. With a head like a T-Rex and a body like a long-legged crocodile, Opisthosuchus is a brutal killing machine. The top dog carnivore of its age. The importance of these footprints is that there are so many of them. And they fit with another clue found further down the valley. The unmistakable signs of ancient water ripples, long fossilized in solid sandstone. Comparing the direction of the footprints in the sand and the direction of the rippling water produces an obvious conclusion. The reptiles were walking along a beach.
The time these two creatures lived, it was the very beginning of a new ocean, and actually the animals were walking along a new sea.
The Tethys Ocean is created. Pangaea is no more. And Europe is born. This new discovery gives Lionel a window into how Europe formed.
When I discovered the site, I really realized that it was something very, very important for us, because here we have much more information. We can follow the track rays along long distance, and this is very, very new for Swiss science and actually for the paleontological science as a whole.
It's a breakthrough in our understanding of Europe's past. And Lionel's research will continue to shed light on the continent's earliest days. But it's vital that he preserves this new evidence. Wind and water constantly weather away the rock. These footprint clues to Europe's origins could be lost by the end of the century. The Tethys Ocean splits Europe apart from Africa and South America. But one other landmass still clings to its western border. Before we recognize it as modern Europe, the continent has one more weight to shed: America. The notion that Europe and America had once been as one was first mooted almost a century ago. Fired by the realization that North and South America's coastlines fitted perfectly with those of Africa and Europe. The obvious conclusion: they'd once been joined. The missing piece was the 5,000-kilometer-wide ocean now separating them. Clearly, some immense force tore the continents apart. Clues as to what that force could be come from Europe's furthest outpost, Iceland. This 500-kilometer-wide island, set in the Atlantic Ocean, defines Europe's western edge. A barren, alien landscape forged by fire and ice. For its 300,000 residents, life is a battle against the elements. But for scientists, Iceland is a geological treasure chest of clues to Europe's history. Dr. Evgenia Ilianskaya of the Icelandic Meteorological Office studies the origins of Iceland. Her research leads her to Thingvellir Valley in the southwest of the country. The only place on Earth where you can walk in the rift between two continents. Everywhere are massive tears in the ground. Something is splitting this valley in two, a force capable of prizing Europe and America apart.
It's hard to imagine what kind of force has the power to move continents and oceans.
The first indications of the answer to Evgenia's riddle came with the development of sonar in World War II. Sound navigation and reading bounced sound waves off the ocean floor to produce a 3D map of the seabed. In the Atlantic, it found more than oceanographers had expected. A 16,000-kilometer-long string of submarine volcanoes is erupting along the center line of the Atlantic Ocean. Scientists naturally called it the Mid-Atlantic Ridge. This huge scar zigzags across the crust like a knife wound, separating the Americas from Europe and Africa.
The two tectonic plates are being pulled apart by very powerful currents deep down in the Earth. And in fact, it's happening right now, about 10 or 15 kilometers beneath my feet.
Hot, molten rock explodes through the ocean floor, forming new land. This wedges the two adjacent continents ever further apart. Over millions of years, the result is inevitable: the 5,000-kilometer-wide Atlantic Ocean. 98% of the ridge lies under the sea. One of the very few occasions when it lifts its head above water is to run straight through the center of Iceland.
Right here, I'm walking in Thingvellir Valley. This is the only place on Earth where you can walk between two continents, America on this side and Europe on the other. This rift continues on through the Atlantic for thousands of kilometers.
Thingvellir is tranquil today, but the two sides of the valley are still, oh so slowly, pulling apart. 2 centimeters of movement a year promise volcanic chaos in the future. Evgenia is walking through one of the most geologically active areas on Earth. The devastating outcome of what happens when the rift stretches to breaking point is still branded on people's memory. Some 200 years of silence is finally shattered as northern sections of Iceland's rift tear apart. The ground pumps out fountains of lava, 4.5 kilometers long. The Earth's onslaught is just beginning. Krafla's eruption will endure for 9 years. It is only with the birth of the Atlantic Ocean that Europe begins to look like Europe. But continental movements have yet another surprise in store. They're about to create southern Europe's most iconic geological feature: the Alps. 1,200 kilometers long, 200 kilometers wide, and spanning 11 countries, the Alps are the great divide between northern and southern Europe. More than 80 peaks soar above 4,000 meters, and the land is still rising. Yet the majority of alpine mountains only formed 30 million years ago, a finger snap in geological time. For centuries, scientists have debated how they were made. One of the first suggestions came from Leonardo da Vinci. The famous artist was also an architect, an inventor, and a questioning scientist. Long before the Mona Lisa, da Vinci grew up in the foothills of the Apuan Alps. He was mesmerized by their grandeur. On an alpine expedition, he found fossilized sea creatures high up in the mountains, yet more than 300 kilometers from the sea. The all-powerful 15th century church claimed the fossils as evidence for Noah's flood.
Genesis. The flood was 40 days upon the earth, and all the high hills that were under the whole heaven were covered.
The marine remains had reputedly been deposited on high as the biblical floodwaters subsided. But da Vinci suspected differently. He noted that his fossils were in distinct layers, with individual species clustering together as they might in the sea.
If the shells had been carried by the muddy deluge, they would have been mixed up, and not in regular steps and layers as we see them now.
He speculated the fossils had formed under an ocean, but even the great Leonardo could not work out what force could possibly push the bottom of a sea up into the Alps. Swiss geologist Sean Willett is following in the footsteps of Leonardo da Vinci, trying to explain why a seafloor has ended up thousands of meters inland.
So I've come up out of the valley now, and the geology here is starting to change. Down in the valley we could see very distinctive continental rocks. Here we're starting to see marine rocks now. Today they're high in the Alps, but these would have once been the floor of the ocean.
Only one force is strong enough to lift the floor of an ocean up a mountain.
Looking at a magnificent mountain range like the Alps, we get a good feel for how powerful the forces are that create these sorts of mountains. The Europe that we see today is the result of multiple continental collisions. The youngest of these is the one we see today in the Alps. No collision, no continent.
The evidence of this collision is all around. Layers of rock upended, folded, and bent.
We think of rocks as being hard, solid objects, but given the powerful forces that we have during continental collision, and given the long time over geological times, this rock can be broken, it can be faulted, or it could be folded.
But if the Alps were uplifted due to a huge collision, which continent crashed into Europe? The answer lies entombed in one of the Alps' most famous landmarks, the Matterhorn. At 4,478 meters, this instantly identifiable mountain straddles the Swiss-Italian border. 500 people have died climbing its treacherous slopes. But hidden within its geology lie clues as to which collision created the Alps. To find them, Sean Willett is heading up the Matterhorn. Sunset, the 3,000-meter mark.
When you get up here at this height, the geology is very spectacular. We're really in the Central Alps now. We're in the heart of what is really the continental collision that occurred here some millions of years ago, and that's what really has given rise to this spectacular topography. There's nothing like a continental collision to set the dramatic backdrop to scenery like this.
Tomorrow, the final push.
We're coming up to the steep section now.
Though Sean's not going to the top, he faces a hard climb. He's taking a researcher to see the secret that even Da Vinci never imagined.
This is the start of the climb. We can put on our harnesses here.
500 meters above them lies the evidence they've been seeking. There's a remarkable change in the rock.
So we've reached the high point of our climb. We've been walking up through oceanic rocks, but now we've reached what are clearly continental rocks. Everything from here up to the summit of the Matterhorn is now continental rock.
When geologists traced the origins of this layer, they were dumbfounded. The rock capping one of Europe's highest peaks was alien to Europe. It came from a totally different continent, 1,000 kilometers to the south, Africa.
So in a matter of a few short kilometers, we've managed to traverse an entire ocean basin from the European continent to the African continent, and that's pretty remarkable.
The Alps formed because ancient Africa collided with Europe. Alpine rock formations show what happened 80 million years ago. Africa pushes north towards Europe, crushing the Tethys Ocean between them. The Africa plate plows on into Europe, piling up oceanic sediments in slices. Those layers stack up in front of the geological bulldozer that is Africa, until part of Africa scrapes off the top and rides up over the oceanic sediments.
And the entire pile was then put on top of the European crust.
The Matterhorn's geological sandwich of 3 different rocks reveals the history of the Alps. European continental rock as its foundation, oceanic rock in the middle, and perched at the top, Africa. Africa's tectonic car crash created the landscape of southern Europe. But as continents continue moving through the eons, there's another transformation in store. 6 million years ago, the day before yesterday in Europe's long history, a cataclysmic event vaporizes its most iconic sea, the Mediterranean. Today, this turquoise jewel defines the continent's southern edge. Its dramatic coastlines and white sand beaches make it the most popular tourist destination in Europe. Its clear waters teem with life, giving food to millions. Regarded as the crucible of Western civilization, its own history has been far from civilized. Geophysicist Ramon Carbonell grew up beside the Mediterranean. Today, he's a geological detective on a mission to tell its story. His investigation leads him to Sorbus in southern Spain. This scrubland landscape gives nothing away. To find what he's looking for, Ramon is going to have to search the Earth itself.
Check me out, okay?
This 1 meter wide hole is his gateway into the ancient Mediterranean. It's leading him back in time to an event that transformed the sea into a dust bowl. This cavern is part of a network of tunnels stretching 50 kilometers underground.
Wow, this is what I wanted to see. Gypsum stalactites.
Gypsum is a form of calcium sulfate laid down as salt water evaporates. Normally translucent, the gypsum here is so clear it made the window panes of ancient Rome. Deposits in these tunnels run to a depth of more than 160 meters. Ramon is walking through the ancient salty remains of a dried-out sea. But what inflicted such a catastrophe on the ancient Mediterranean? It is 6 million years ago, and Africa slams into Europe, lifting southern Spain. The collision eventually cuts off the Mediterranean from the Atlantic. In this hot climate, water evaporates from the basin 10 times faster than rivers or rain can refill it. Sealed off from the replenishing waters of the Atlantic, the sea level drops lower and lower, leaving fast-flowing rivers that carve out deep canyons. The valleys of Europe's largest rivers now resemble Arizona's Grand Canyon, only larger. 3,000 cubic kilometers of water evaporate each year, leaving behind a thick, soupy layer of salt and gypsum up to 3,000 meters thick. In just a millennium, the Mediterranean is transformed into a dry basin of salt pans and caustic lakes. And yet, this ancient dust bowl somehow became the majestic sea we know today. Ramon wants to understand how that happened. He's heading for Europe's southern tip, where clues can still be found. The Straits of Gibraltar, gateway to the Mediterranean. Guarding the entrance to the Atlantic, this strategic point has been fought over for millennia. At the Rock of Gibraltar, just 14 kilometers of open sea separate Europe from Africa.
About 6 million years ago, the scenery that we are seeing behind me, it was not the same one. There was a land bridge connecting the European continent with the African continent, actually blocking the Mediterranean Sea in a similar way that the gigantic geological dam would do.
That link between Europe and Africa survived for tens of thousands of years, until suddenly it disappeared. The last act of this geological drama mystified scientists for centuries. Greek mythology offered an answer. Hercules stamped his mighty foot to make a passageway. In 77 AD, the Roman elder Pliny came up with a more likely explanation. The Atlantic was to blame.
The sea, which was before excluded, gained admission, and so changed the face of nature.
The landscape of Europe has all the geological mysteries you can imagine, but it also has its answers.
To find evidence of how the modern Mediterranean took shape, Ramon must look beneath its waters. He's heading out into the Straits. Using 3D imaging technology, he's mapping the shape of the seafloor. Entering the center of the Straits, the depth readings suddenly change.
This is the part where the seafloor just drops down dramatically from 40 meters to about 900 meters. So there's a very steep slope. So we're going into a valley, into a channel.
Ramon is directly above a steep underwater canyon.
That's the gray area here.
This is where the dam between Africa and Europe gave way. 5.5 million years ago, Africa thrusts northwards into Europe, raising sea levels. Erosion by rivers has weakened the intercontinental dam. The wall of rock, still holding back the Atlantic, reaches breaking point. A torrent of water nearly 1,000 times larger than the outflow of the Amazon pours past Gibraltar every day. The 2.5 million square kilometer basin is refilled by the Atlantic in less than 2 years. And the 200-kilometer long channel that Ramon has identified was gouged out by that enormous flow of water. The Mediterranean, defining Europe's southern border, is finally in place. As Europe nears the end of its time travel towards the present, for once, all seems quiet. But the calm waters conceal a deadly secret. A geological monster stirs beneath the surface. Africa's collision with Europe has a dramatic side effect. Rocks forced deep under the continent melt into magma. A volcano is born. Stromboli. The 900-meter-high island we see today is just the tip of the iceberg. Its slopes continue down for 1,300 meters to the bottom of the Mediterranean. Thousands of years of near-constant eruptions have built up this mountain from the seabed. Geologist Nick Petford is investigating how volcanoes like Stromboli continue to shape Europe.
So volcanoes are like spectacular fire machines in one respect. But of course, the lava has to get to the top of the volcano in the first place. And what I'm interested in as a geologist is to understand the magma plumbing system.
Offering sun, sea, and spectacular eruptions 24/7, Stromboli is a place of pilgrimage for lava lovers from around the world. Yet few tourists realize that the lava bursting out of this volcano is molten Africa.
If you look up there now, you can see it's puffing. This volcano is in a constant state of eruption, and that's why it's so exciting to be here, but we want to get up close and take a real detailed look.
As the sun sets, Nick finally reaches the summit.
We're here now at the top of the summit of Stromboli. It's just getting dark, and you might think it's a bit odd to come up to a volcano at night time, but the reason we come up in the dark is because that's when we get the best view of the kind of volcanic activity that takes place here. We're definitely in the hazard zone now. I'm just going to get into the suit and see if I can get a bit closer to see what's going on down there.
His aluminium suit will protect Nick from heat of up to 900 degrees Celsius. But the deteriorating weather is a risk he can't control.
The mist is coming in now, but I've got one chance to go and have a quick look at the lava. I can see it down the crater.
Stromboli has an eruption style all of its own. Gas explosions throw lava 10 times hotter than boiling water high in the air. The result, stunning Strombolian eruptions.
Well, I managed to get down there quite close to where the vent was, but the mist has rolled in. I got some measurements and managed to see some good stuff, but now the mist is there and it's just this really eerie, quite scary environment where you can't see the spatter until it's nearly too late. So it's just too dangerous to be here, so I think it's time to go.
By day, Stromboli seems placid enough. But like all volcanoes, it's prone to mood swings. Over the last 100 years, Stromboli has flung out everything from pea-sized pumice to 2-ton fireballs.
One of the remarkable things about the 1930 eruption of Stromboli was the power and the veracity. Blocks the size of this vehicle were thrown for hundreds of kilometers from the vent, which then came crashing down on the mountain.
Stromboli sits in the wide collision zone between Europe and Africa. And to Nick, its presence signals only one thing: subduction.
So behind me, out beneath the Mediterranean Sea, something quite remarkable is happening, and that's a process called subduction. And here we have the African plate, which is sinking down beneath the European plate. And it's sinking down because the African plate is just a bit more heavy. And as it sinks down, it starts to cause melting in the Earth's mantle. And those sites of melting at the surface of the Earth are expressed as volcanoes.
80% of the Earth's surface is formed by volcanic activity, and it shows no sign of stopping. With the African plate still forcing its way underneath Europe, its deadly side effects will continue shaping the landscape.
New volcanoes will be forming. In fact, under the sea now, there are smaller volcanoes on the sea floor, and in future they will break surface and form new land.
These volcanic firework displays are the magnificent finale to Europe's most recent continental collision. For eons to come, Europe will continue to be shaped by the movement of the Earth.
Future geologic events are impossible to predict, but we do know that tectonics operates on a cycle. Oceans open, continents come together, they collide, we build mountains, those mountains stop building, they erode, the erosion breaks those mountains down to nothing.
The future battles faced by this complex continent will be written in her rocks.
One thing we do know is that it will constantly change. And so the Europe of the future will be very, very different from the Europe of today.
Continents continue to move around the globe. Sooner or later, they will collide again. Another supercontinent will form. And Europe as we know it will be lost forever.